Good morning. I am Dr. Ravi Ammiraldi, Professor and Head of the Department of Electronics and Communication Engineering, SZ Balekundri Institute of Technology, Belagavi. Today we shall continue the discussion on bipolar junction transistor. Last class we have seen, right, we have discussed about the significance of the term BJT. BJT means bipolar junction transistor. The term bipolar indicates the involvement of the holes and the electrons in the conduction of the current. That is why the term bipolar. Bi means two, polar means the charge carriers. So, here in the BJT the current is contributed by both the holes and electrons. Junction. The term junction, it represents the, since the bipolar junction transistor is having two junctions, one is the between the emitter and the base, another between the collector and the base. So, that is why the term the junction is being used here. The third term that reflects, that is transistor. So, that is the transistor means it is transfer plus resistor or transfer of resistance. So, whenever the AC signal is applied across the transistor, the AC signal is transferred from low resistance region to the high resistance region. Here, as you can see here, in a PNP transistor, the P plus, that it acts as the emitter, and N minus it acts as the base, and P layer it acts as the collector here. So, usually the emitter base junction, that is input junction, is forward bias, and the output junction, that is collector base junction, is reverse bias. So, when the input junction is forward bias, so that will provide a low resistance region, and when the collector junction is reverse bias, it provides the high resistance. So, in addition to this, whenever an AC signal is applied across the input junction, this AC signal is transferred from low resistance region, that is emitter base junction, to the high resistance region, that is the collector base region. That is why the name transistor here. And also we have seen the BJT, bipolar junction transistor, it consists of three layers, that is emitter layer, base layer, and collector layer. In fact, there are two types of BJTs are there. One is PNP transistor, another is NPN transistor here. So, the P, if you consider the case of the PNP transistor, the P plus it acts as the emitter, N minus it behaves as the base layer, whereas the P will be the collector here. Compared to the emitter and the collector region, the middle region is very thin compared to other region, whereas the P plus layer, which forms the emitter, it is having more width compared to other, whereas the P layer, which is nothing but a collector, it is having the width in between that of the emitter and base. In addition to this, you need to know the doping concentration of each layer here. The plus indicates the P layer, that is emitter layer, is heavily doped, and N minus, that is base layer, it is lightly doped, whereas P, that is the collector layer, which is the moderately doped. That means the doping concentration of the P layer, it is in between that of the emitter and the collector here, emitter and base. And also we have seen in the last class the operation of the bipolar junction transistor. As you can see in this slide, we have a PNP transistor. The P, it forms the emitter, N region or N layer, it is nothing but the base region, and the P layer, the extreme right hand side P layer, it forms the collector here. And also you can see that the emitter, that is nothing but P layer, is connected to the positive terminal of VE and with reference to base, and similarly the collector, that is nothing but P layer, it is connected to the negative terminal of VCC with reference to the base. Therefore, the emitter base junction is forward bias. Similarly, however, the collector base junction is reverse bias. As you know that, as you noted down in the semiconductor junction theory, whenever the junction, any device is either forward bias or reverse bias, there will be a depletion region exist across this. So, as you know that the emitter base junction is forward bias and the collector base junction is reverse bias. So, usually the thickness of the depletion layer exists across the collector base junction is more compared to that exists across the emitter base junction. So, therefore, as you know that we have a PNP layer here. In P layer the majority charge carriers are holes, in N layer the majority charge carriers are the electrons here. So, therefore, whenever we connect the P layer to the positive terminal of the VE, so these electrons the holes they get repelled by the VE, positive terminal of the VE, they will be diffused into, they will cross over the depletion region and moved into the N layer. When these holes they move from P layer to N layer, some of these, that is about 5% of these holes, they recombine with the electrons of the base layer and that will contribute the base current, and remaining 90%, so they will move across or they will diffuse from the base layer into the collector region. So, because you know that once the majority carriers of the P layer, that is holes, when they diffuse into the N layer, they act like a minority carriers. Therefore, as you know that there is a depletion region existing across this particular collector base junction, and due to that depletion region there will be potential barrier exist, and this potential barrier it will be favor these electrons or these holes to move from the base layer to the collector layer, and therefore that will contribute to the collector current. So, and also apart from that, so we have also seen some of the BJT voltages and currents that is existing in the device. Here, as you can see that this is the symbol for the PNP transistor having the emitter base collector, and also the arrow it indicates the emitter current, base current and the collector current. So, as you can note on from this symbol PNP, the I is nothing but the IB plus IC. Similarly, if you apply KVL to this, we will get the VEB equal to VEC plus VCB. From this you can derive that VEC equal to VEB minus VCB here. Similarly, for NPN transistor you can see that, so we have emitter terminal, base terminal and collector terminal with the arrow indicating the various currents, that is emitter current and base current and the collector current. So, and also you know that the voltage existing between the base to emitter, it is represented by VBE, and that between the base and collector represented by VBC, and the voltage appearing across the collector to emitter, it is represented as VCE. If you apply KVL to this, so we will get VBE equal to VCE plus VBC, and from that we can deduce that you can note on that VC equal to minus VBC plus VBE. And also in symbol we have noted that the arrow, whatever arrow you can see that represents the emitter here. From this the symbol of PNP you can see that the arrow is over here. So, therefore, this terminal represents the emitter, whereas in case of the NPN transistor, so this terminal is having arrow. So, therefore, this terminal is called as the emitter, and always you should note that. So, always this arrow it will be towards N layer. So, in the case of this PNP transistor, this is the emitter is P and base is N and collector is P. Therefore, now the emitter current it will be from the emitter to base, that is towards N region. Similarly, in the case of the NPN, we have the N acts as the emitter, P will be the base region, whereas the N will be the collector region, and therefore, here you can see that the current, the emitter current, it is towards once again from base to emitter, that is P to N here, that is. So, that is what you can note on from this slide. And also we have noted down the semiconductor junction, either it can have a forward bias or a reverse bias. So, there will be a combination of the forward bias and the reverse bias case. So, depending upon the suitable combination of this, the forward bias and reverse bias, the BJT can operate in either of active region, cutoff region and saturation region. If both the junction, that is the emitter based junction and collector based junction are reverse bias, then the transistor is said to be cutoff region. If both the junction, emitter based junction and collector based junctions are forward bias, then transistor is said to be saturation region. In case the emitter junction, the emitter based junction, that is called as input junction, is forward bias, and the collector based junction, if it is reverse bias, then transistor is said to be in active region. And depending upon the which region it is operating, the bipolar junction transistor is operating, so we can use either the BJT either as an amplifier or logical switch. Usually whenever the transistor operates in active region, it is being used as an amplifier. In case of the logic switch, so we can make use of either the cutoff region or saturation region. So today at the end of the session, you will be able to solve some problems related to bipolar junction transistor, and also you can able to note down the differences or three basic configuration of single stage bipolar junction transistor amplifier, that is BJT amplifier, and also you will be able to analyze the common base characteristics of the BJT. So, and at the end of the session we shall see how the BJT acts as an amplifier in using the common base configuration. So now let us see the from this figure we have a PNP transistor. So that's what that you can note down from the emitter terminal here. So emitter terminal, the arrow is always towards the N type. So therefore this transistor, given transistor, is PNP here. So this P acts as the emitter, and this N, it acts as the base, and the P, other P layer, the extreme P layer, acts as the collector here. So from this you can note down that emitter base junction is forward bias, because P layer, that is emitter, that is connected to positive terminal of this supply with reference to the base. Similarly, the collector base junction is reverse bias, because collector, that is nothing but the another P layer which will be connected to negative terminal of other supply here. So therefore emitter base junction, that is input junction, is forward bias, whereas the output junction, that is collector base junction, is reverse bias. So from this figure, right, if you apply the Kirchhoff's current law, we can note down that IE equal to IB plus IC there. So therefore if we can derive this equation, we will be noting down, that is, one is from this equation, from this if you apply the Kirchhoff's current law, we will get the input current equal to, that is emitter current, equal to IB plus IC there. So here we know that the one parameter called as the alpha DC. So it is nothing but the ratio of the IC by IE. That means it is also called as it is called as common base current gain or DC current gain. So here the current gain, as you know, that it is a ratio of current by current, is it not? Gain means it is a ratio of output by input here. In this common base configuration, please note that the collector current acts as the output current, whereas the emitter current acts as the input current. Therefore alpha DC, that is nothing but the common base DC current gain, it is the ratio of the collector current to the emitter current here. So therefore from this we can see that, so the IC is equal to alpha times of DC, that is DC current gain into the emitter current here. So from this if you substitute over here, what I will get? Alpha DC, this into IE. IE is nothing but the summation of the base current, right, plus IC there. So therefore from this I can write it as alpha DC into IB plus alpha DC into IC there. So therefore if I can rearrange this equation, we will get IC. So this term I can take it to the left side. So this will become alpha minus alpha DC into IC there is equal to alpha DC into IB there. So therefore, here I can take IC common there. So therefore, from this IC is into 1 minus alpha DC. So that equals to what? The alpha DC into IB there. So therefore, from this I can say that IC will be equal to alpha DC divided by 1 minus alpha DC. So into IB there, or this I can rewrite as beta DC, right, into IB. So where beta DC is, what is beta DC here? Beta DC is nothing but it is common emitter current, DC current gain, DC current gain. Okay, once again here this is a current gain similar to the alpha DC, but thing is that here once again, as you told that it is current gain, it is a once again ratio of the output current by the input current in case of common emitter configuration. In if common emitter configuration means emitter is common to both input and output. So here input is IC, the collector, and output is the base. Therefore beta DC it is equal to the ratio of IC by IB. So therefore, this from this we can say that so beta DC is equal to is nothing but alpha DC divided by 1 minus alpha DC. So that is what we can make a note of this. So this is what, okay, we will get the common emitter DC current gain in terms of common base DC current, that is alpha DC there. So now let us see, let us solve some of the one or two problems using this. So first problem statement, it says that calculate the IC and IE for a transistor that has alpha DC, that is common emitter, common base DC current gain, that is, and that is equal to 0.98, and the base current is equal to 100 microamperes. So we need to determine the value of beta DC or HFE of the transistor here. Now let us see the mainly let us solve this problem, right. So we shall see what exactly the solution for this problem. So what is asked here? We are need to given here, so the solution is okay. We need to, what is the given? Given is alpha DC is equal to 0.98, that is the common base current gain, and IB, that is base current, is given as how much? That is 100 microamperes. So using these two data we need to calculate the IC, okay, then IE, okay, and then the beta DC or HFE there. It is also called as HFE. This we need to calculate. So therefore, what is the answer? Answer IC we know that in terms of alpha DC and IB here. So therefore, it can be given as alpha DC by 1 minus alpha DC into the IB there. So from this we can say that this is nothing but 0.98, okay, divided by 1 minus 0.98, okay, into the IB. IB is 100 microamperes. So if we substitute this, we can able to get the answer there, that is approximately this will be equal to this is 0.98 divided by 0.02, this is into 100 microamperes. So this amounts to be, so this is 49, okay, into 4900 microamperes, or otherwise I can say it as 4.9 milliamperes. So that's the answer for the collector current. Similarly, IE you can note down as I is nothing but what? The input current, it is summation of IB plus IC there. IB is given there, IB is, it is given as 100 microamperes plus, okay, IC is calculated as 4.9 milliampere. So this comes about, this is 5 milliampere there, 4.9, this will be around 0.09, this will be around 4.9, this is 100 microamperes, IB is 100, IC is calculated as 4.9 milliampere. So this comes about 4.9 into, you can say this is nothing but in terms of the 100, I can calculate as 10 raised to minus 3. So this will be how much? This will be 0.1. So 0.1 means it 0.1 milliampere, this will be 5 milliampere. So therefore we can say that I is almost equal to IC there, and finally the beta DC we need to find out. You can simply make use of either using this alpha DC by 1 minus alpha DC, okay. So this is nothing but, so if you substitute there, okay, 0.98, 1 minus 0.98, this comes out around how much? It will be 49. So that is what we are getting. So therefore using this okay, solution, we get IC equal to 4.9, I equal to, naturally it is 4.5 milliampere, we are, and beta DC is nothing but the 49 there. So that is what you can see here. So IC is calculated using this, we have got it 4.0 milliampere, I is 5 milliampere, and beta DC is 49 here. Now let us see the another problem here, okay. So once again here the statement, problem statement is calculate alpha DC and beta DC for the transistor if the collector current is 1 milliampere and the base current is 25 microampere. We need to determine the new base current gain to give IC equal to 5 milliampere. Now let us see, right, how we can able to solve this particular problem. So what will be the solution here? Now let us note on what are the given things. What is okay, given is, so is IC, the collector current is given as the 1 milliampere, and so and IB, the base current, is given as 25 microamperes, okay, and we need to determine alpha DC to determine alpha DC, okay, and beta DC, okay, and so after that we need to determine the new beta DC. So therefore beta DC new, okay, for that for a collector current of 5 milliampere. So this is for collector current of 5 milliampere there. So to get alpha DC, what is alpha DC? You know, this is nothing but the IC ratio of output current, that is collector current, to the input current. So but IC is given, I is not given, but however IB is given. Therefore what I can do is IC divided by this, I can write it as IB plus IC there. So therefore IC is given as 1 milliampere, okay, this is 1 milliampere, and this IB, so this is 25 microamperes plus how much? This is 1 milliampere. So this will get around, this is 1 milliampere and 1.025 milliampere there. Similarly, using this alpha DC, so that is what you can see here. So what we have done, okay, we have used either this IC by IB there. So this comes around 0.976 there. Similarly, we can use the beta. Once you get beta, so right, once you know alpha DC, so you can directly write alpha DC, or otherwise you can use the ratio of IC by IB there. So, IC you know it is 1 milliampere, and base current you know that is 25 microamperes. So, therefore, this I can write as 1 milliampere divided by this is 0.025 milliampere. This comes around 40 as the common current. Common, okay. So, emitter DC current gain, that is what we are getting. So, finally, using this data, so finally what you need to do, beta DC nu. So, therefore, beta DC nu will be, as you know that this is once again that we have used, okay. So, from beta DC nu for IC equal to this. So, therefore, beta DC is nothing but IC by IB there, okay. So, beta DC is IC by IB. So, for IC 5 milliampere, so what is IB, it remains same, okay. You will get, you will able to get the answer using this. So, that is comes around the. So, this is how you can able to solve the, okay, the two problems related to both transistor current and voltage equation there. Now, let us see some configuration of the bipolar junction transistor. So, as you know that the in the two port networks, they are having two input ports and two output ports. So, but however, the bipolar junction transistor is having three terminals. In order to fit this bipolar junction into the two port networks, so one terminal has to be made common here. So, therefore, that is why it results in three configuration of bipolar junction transistor. So, therefore, here you can see that these are the, okay, emitter we have got as the input and collector as the output, and therefore, in this case the base is common, okay, with reference to both input as well as the output here. So, similarly, in case of this common the emitter configuration, you can see that the emitter is common to both input, that is base here, and with reference to output, that is the collector. Similarly, in this particular okay, circuit diagram, you can see that the common collector configuration, collector is common with reference to both input, that is base, and the output, that is emitter there. Now, let us see the in detail the common base configuration of bipolar junction transistor. Here we are considered an NPN transistor. So, this N acts as the emitter, and the middle layer it acts as the base, and this extreme right layer N layer acts as the collector there. So, in this case you can see that emitter, that is N layer, is connected to the negative terminal of the BBB with reference to base. So, therefore, emitter base junction is forward bias, whereas the collector base junction, that is collector means this N, okay, extreme right N, it is connected to the positive terminal of the VCC with reference to the base, and therefore, this will be reverse bias. So, please note that in common base terminology or common base configuration of BJT, the base is common to both input and output. Input here is emitter and output will be the collector there. So, base is usually the terminal closest to or at ground potential, that is why here you can see that. So, base is maintained at the ground potential here, and also you can note on that all current directions in BJT will refer to conventional flow, that is the conventional direction of hole flow. That means, it is against the direction of the electron flow, and the arrows in all electronic symbols have a direction defined by this convention only, that is conventional current flow here. Note that the applied biasing are such as to establish the current in the direction indicated for each branch. Therefore, here you can see that we have a common base configuration for both PNP as well as the NPN transistor. In PNP transistor, you can see that this P acts as the emitter, this N acts as the base layer, whereas this P acts as the collector layer. Therefore, in this case, so this P is connected to positive terminal of the VE with reference to base. So, this is forward bias, whereas in this the output junction, that is P layer, that is collector, it is connected to negative terminal of the VCC with reference to the base. So, this will be reverse bias. So, similarly, in case of NPN, the emitter base junction is forward bias by connecting N layer, that is emitter layer, to the negative terminal of VE, right, with reference to the base, and on the other side the collector, that is nothing but extreme right N layer, it is connected to positive terminal of the VCC with reference to the base here, and therefore it is reverse bias. That is what it can be seen here over, okay, in this common base configuration symbolic notation. So we need to write, in order to explain the behavior of common base amplifier, we need to study, right, the both input and output characteristics of the BJT in common base configuration. Input, because since the base is common to both input as well as the output, okay, so this is called as common base configuration. Here in this common base configuration, emitter acts as the input terminal, whereas the collector acts as the output terminal here. So this is whatever you can see on the left side of this slide shows the input characteristics of the common base transistor, common base configuration of the BJT. So wherein graph is plotted between VBE, that is input voltage, versus IE, that is input current, keeping the VCB constant, that is VCB means the output voltage here. Similarly, you can see on the right side of this slide output characteristics, wherein the VCB, that is the output voltage, that is plotted against the output current, that is IC, keeping the input voltage, that is IE, constant there. So now let us take up one by one characteristics, and we shall see, right, how we can able to analyze the input characteristics. So this particular slide shows the input characteristics of the bipolar junction transistor, wherein VBE, that is input voltage, is plotted, okay, against the emitter current, that is in the input current, input voltage versus input current, keeping output voltage constant here. So that is nothing but the input characteristics of the common base configuration of BJT here. So what is evident from this? So you can note that, so the emitter base junction, it is forward bias. So therefore the whatever the input characteristics of common base configuration, it is almost similar to that of the forward biased PN junction here. So therefore here you can see that until the VBE, that is input voltage, becomes equal to the cut-in voltage, okay, the current will be 0 here. When VBE exceeds the cut-in voltage, as you know that it is 0.7 volt in case of silicon transistor, it is 0.3 volts in case of the germanium transistors. So once the input voltage VBE exceeds the cut-in voltage or threshold voltage, then so the current will start flowing through the transistor there. So and another point you can note down that, so for a given VBE, more current flows when higher levels of VCB are used here. So if you want to know this particularly, just let us see. So here you can see that, so whatever for constant, if you take up one vertical this one, so you can see that for a constant fixed value of VBE, if you draw for, let us assume that VBE given is 0.8 volts. So therefore corresponding to this VBE, if you draw a line here, let me see the line ಹಾಕಬೇಕು. ಇಲ್ವದು So friends, you can note on that one conclusion what you can draw is, when emitter base junction, that is input junction, is forward bias, the input characteristics are essentially similar to that of forward bias PN junction. That's what you can, I said. So until the VB becomes equal to the cut-in voltage or threshold voltage, the current will be 0. When it exceeds the cut-in voltage, the current will start flowing through this. So other point what you can note down here, so is with regard to, for a given VB, if you draw a constant, okay, let us assume that given VB is, okay, the is 0.8 volts, and if you write corresponding, if you draw the emitter current, you can see that what you can observe, for a given VB, more current, that is IE, flows, right, when higher levels of VCB. So therefore whenever this VCB increases, okay, and for a given fixed value of the VBE, whenever the VCB increases from 1 volt to 20 volts, correspondingly the emitter current increases. The reason being is that VCB, as you know, that it is a reverse bias applied across the collector base junction. So therefore whenever the collector base junction increases, the width of the depletion layer existing across the output junction increases, and therefore, so what happens, the more the depletion layer that is existing across the output junction will penetrate into the base layer, and therefore naturally the more more of the majority charge carrier they will be able to swept into the collector junction there. So now let us see, okay, one by one. So now let us see the output characteristics of the common base configuration. Once again, as you can note down here, it consists of 3 regions. One is active region. It is defined by the biasing element, because for in order to have the BJT in active region, we need to have, right, the emitter base junction in the forward bias, collector base junction in the reverse bias here. So then the transistor is said to be the active region. Whereas in case of the cutoff, you can see that the region, whatever region you can see here, okay, in the blue region, that is below the collector current, IC current of 0 ampere, that is nothing but the cutoff region. And whatever region you can see here on the, okay, to the left of VCB equal to 0, so that region we call it as the saturation region there. So once again here what you can note down, for each fixed level of IE, so okay, IC is almost equal to IE there. So therefore that means, okay, that means IC appears to remain constant when VCB increase. That means, so IC, the output current, it is independent of the output voltage, that is reverse bias applied across the collector base junction here. So that, because you can see this, right, when this VCB is increased from 0 to 25, right, you can't find, right, almost this the current curves almost it is flat. So there is no much variation here. That means what, the increase in VCB is not having much effect on the output current, that is collector current. So it is but however, if VCB exceeds the 25 volts, so there might be a breakdown here, and because of this breakdown mechanism, what happens, the collector current, output current suddenly decreases here. So it happens because, mainly because at whenever this VCB exceeds the 25 volts, so these both the depletion region, one existing across the input junction, other existing output junction, they get close together, and therefore a large current flows through the device here. And another point, what you can note down here at this edge here, at this, whenever VCB is reduced to 0, IC still flows. Here at this point, you can see that when VCB, for corresponding to VCB 0, still there is a finite amount of the collector current is flowing. The reason being, because even okay, when there is no bias across the collector base junction, VCB 0 means what, there is no bias across, reverse bias across this. For VCB equal to 0, there is no bias, but still you know that under the no bias condition, still there is a depletion layer exist across the collector junction, and this will, because of this, okay, so there will be a current flowing through the BJT device here. And in order to reduce this collector current to 0, here if you want to reduce it to 0, what you need to do? We need to forward bias, okay, the collector base junction. We have to reverse the potential, the terminals of the mainly the voltage supply, there power supply. If you are able to reverse interchange the terminals of this, so then accordingly the collector base junction will be forward bias, and what happens, the collector junction will reduces to 0 there. So this is the three reason what we are defined in case of the common base configuration. One is active region, saturation, and cutoff region. Active region, you know that the input junction is forward bias, the output junction is reverse bias, and here IC it do not depend on the VCB here, because we are having a flat current graph or a plot. So therefore this is the suitable region, right, that is being used for transistor as an amplifier there. Whereas in saturation region, in both input and output junctions are forward bias. So and also you know that whenever there is a small change in VCB, and it will cause a big changes in the output current, that is collector current here. So therefore this region will be the to the left of the VCB equal to 0. So whatever region is there, that is called as the saturation region, whereas the cutoff region is the region below the line or below the current graph of I equal to 0 here. In this case both input and output junctions are reverse bias, and no current flows whenever the device in cutoff region, or maybe only a leakage current may be flowing, which is in the range of almost microamperes there. So the output characteristics clearly indicate the first approximation to the relationship between IE and IC in the active region, and is given by IC is approximately equal to IE here. So here we have, since IB is very small in the range of microampere, we have neglected it. So assume that IC is equal to IE there. And also you can note that the once a transistor is in the on state, the base emitter voltage will be assumed to be VB equal to 0.7 volts, as you can see from this particular graph there. So in the DC mode, the level of the collector current and emitter current due to majority carriers are related by a quantity called as alpha DC. This is, as I told you, that it is nothing but the common base DC current gain, that is the alpha DC. It is defined as the ratio of output current, that is IC, to the input current, that is IE there. So therefore using this relation we can write IC equal to alpha DC times of IE plus ICBO. ICBO, as I told you, that it is the current that flows from collector to base, right, by keeping emitter open here. So therefore since this ICBO is very negligibly small, we can neglect it, and therefore what we can deduce is that IC is equal to alpha DC times of IE here. Whereas apart from this common base DC current gain, we have got the common base AC current gain, that is called as alpha AC, which is defined as the ratio of change in output current, that is IC, delta IC, and to the change in the input current, that is delta IE there. So therefore alpha, it is a common base DC current gain, which is a ratio which is a measure of the current that flows from the input to the output here, that is emitter to the collector here. So usually the alpha DC ranges from 0.9 to 0.998 here. So that's what this particular slide shows, the biasing, proper biasing of CB configuration in active region by approximating IC equal to IE here. Since we are neglected IB there, so you can see that the base terminal is floating. So therefore with this arrangement we can able to have the CB configuration in active region there. So and this in CB configuration you can see that here this particular slide shows a PNP transistor working as an amplifier, right, with a applied AC signal of 200 millivolts, and the input resistance is almost very less in the range of 20 ohms, and output resistance is very high. Usually for CB configuration it is high, that is 100 kilo ohm there. This is the input current, this is the output current, that is designated as the IL, or the nothing but the IC there. So, this is what you can see the right how a transistor in CB configuration can act as an amplifier. So, here we have considered an NPN transistor, okay, and this middle layer acts as the base here, okay, and finally this this N layer acts as the input, that is emitter, and this extreme N bottommost N layer acts as the collector, that acts as the output here, which is connected to the speaker here. So, whenever we speak hello, so that will be that signal will be converted into electrical signal, and that will be okay. Its strength will be enhanced using the transistor, and that will be fed to the speaker, which is acts as a load here. So, to conclude, so we have seen in this particular session, right, we could able to derive the expression for the various current, that is one is we know that I equal to summation of the base current and collector current, and also we know that the DC alpha DC is nothing but the ratio of output current by the input current, that is IC by IE, and from this we can see that IC is equal to alpha DC times of IE there. So, here from the equation, if you substitute equation 1 into equation 2, we will get IC equal to alpha, and after rearranging we will get IC equal to alpha DC divided by 1 minus alpha DC into IB there. So, this finally we can arrive at this can be equated to IC equal to beta DC into IB there. Similarly, we came to know about three basic configuration of single stage BJT amplifier. Okay, as I told you that to fit into this BJT into a 2-port network, so one terminal has to be made common. Therefore, if base is made common with reference to both input and output, that will you will get a common base. If emitter is common with reference to the both input and output, it will be a common emitter configuration. Otherwise, in case of collector is common to both input and output, then it gives rise to common collector configuration. And also we discussed about the input and output characteristics of the common base configuration. From this input characteristics is a plot of VBE, that is input voltage versus the input current, that is IE there, keeping the output voltage constant here. So, one thing what is evident from this characteristics, it is similar to the forward biased PN junction, and another conclusion what you can make from this characteristics is that for a fixed value of VBE, okay, whenever the VCB increases, so correspondingly IE will also increase here. It is mainly because of the fact that whenever there is an increase in VCB, then correspondingly the width of the depletion layer existing across the collector junction increases, and it will penetrate more into the base region, and therefore, so more majority carriers will be can be swept into the collector, and thereby increasing the IE current here. So, this is what it is, nothing but the output characteristics. This is the plot of the VCB versus IC, that is output voltage versus IC output current, keeping the IE constant there. So, one thing is that, so irrespective of variation in VCB, there is no effect on the IC there. So, because this particular region is active region, it is almost keeping the constant here, and also usually you know that active region is being used for amplification purpose, because of the fact that because this is a linear region, and another is that there is an equal distance exists between these current curves here, and this equidistance current curves gives rise to faithful amplification. That is one important feature of this active region there. So, that is all. Thank you.